Hi everyone, today I'll show you how to solve the 2015 AP Physics C Mechanics exam FRQ number 1. I do encourage you to pause the video and read the problem, but to save time I will just summarize what the problem says. So basically it says a block is pushed up with initial velocity here, and it goes up the ramp, stops, and goes back the ramp. It does not reach the motion sensor and stops somewhere before the motion sensor and goes back down the ramp. So, and down the ramp is the positive direction, up the ramp therefore is the negative direction. That will be important to remember for this problem. Alright, part A, it says to consider the motion of the block at some time t after it has been projected up the ramp. So for the first part we have to get the acceleration of the block. So let's use Newton's second law to find the acceleration. So we're going to have the net force equals mass times acceleration. And the only force here in the x direction while it's going up the ramp is the force of gravity, which is mg sine theta in the x direction. It's positive because it's going down the ramp. And m's cancel out here, so we'll get that A equals g sine theta. Okay. The second part here says to find the velocity. Okay. Velocity. Let's use our first kinematic equation, which is v final equals v initial plus acceleration times time. Well, let's set v final to just equal to v because that's what they're asking for here. And we'll have v initial, since going up the ramp, that is in the negative direction, so we'll have a negative v initial plus, let's plug in g sine theta from here for A, and then times t. There is our velocity of the block. And for the third part here, part A, it says to determine an expression for the position of the block. Let's use our second kinematic equation here. So which is x final equals x initial plus v initial multiplied by time plus 1/2 at squared. X final, just call that x, equals x initial. It starts at d here at the beginning, so I'll have d, and then again that negative initial velocity minus v initial multiplied by time plus 1/2, plug in g sine theta for A. So g sine theta t squared. X equals d minus v initial t plus 1/2 g sine theta t squared. Alrighty, let's do part B now. It says derive an expression for the position x min of the block when it is closest to the motion sensor. Okay, closest to the motion sensor, which means it goes all the way up and it stops, right? So it's close to the motion sensor. That means its velocity is 0 there. Let's use our third kinematic equation, which is v final squared equals v initial squared plus 2 times acceleration times the displacement. Well, our v final, since it's going all the way up the ramp, or as far as it can go, that's just going to be 0 because it's going to stop there. And then v initial squared, yeah, it is a negative velocity, but it's squared, so we can just say v initial squared. Then plus 2g sine theta for A, and then change in x is x final minus x initial, while our x final is that x min, right? We're going to go all the way to that x min there, and our initial is d, starts at d, so minus d. Let's do some algebra here and solve for x min. So we're going to have x min minus d equals negative v initial squared over 2g sine theta. So x min equals d minus v initial squared over 2g sine theta. There is our x min when it is closest to the motion sensor. Alright, part C. Goes over here. So part C here says basically to just sketch a graph of the position, velocity, and acceleration here. while it goes up and back down the ramp. And sets the label any intercepts, asymptotes, maxima, or minima with numerical values or algebraic expressions. And we only have algebraic expressions here, really, so we're going to use that. Let's do our position here. X on the vertical, T on the horizontal. So here it's going to start at D, right? And D is positive. That's the greatest position it's going to have is D. So let's start that up here, D. Right? And then it's going to be a parabola because the velocity is not constant. There's an acceleration, so it's going to be a parabola. So we're going to start up here at 0, and we're just going to go down with the parabola, but we're not going to get to 0 because 0 is right here. It doesn't get to the motion sensor. It gets somewhere in between, like right before, in that x-min. So we're just going to go down to that x-min, not 0, and we're going to go back up. And this should just extend to t, but you get it. So yeah, it goes back to d. So here goes to 0 and goes, or to x-min, pardon me, and then back to d. So this down here is our x-min. Okay, let's do our velocity now. For velocity here, it's going to start at v initial at that negative value. Eventually it's going up the ramp, which is negative. And it's going to increase to 0. Right, so it's going to go from negative to 0 once it gets up to that, the top of that ramp. So that's 0. And then it's going to go back down, so it's going to increase its velocity now. It's going to have a positive velocity when it's going down, so it's just a straight line there. And that top velocity is going to be v. So let's do acceleration now. So acceleration is the slope of velocity, or derivative, and the slope of this is, well, it's constant. So we're just going to have a straight line here, and it's positive, so it's just going to be some positive slope here. So let's just draw that for our acceleration. That's part C done. Part D, it just says after the block slides back down, it leaves the bottom of the ramp and slides on a horizontal surface. And the horizontal surface has friction, so it has a coefficient of friction of mu k, or just kinetic coefficient of friction. So they just want us to get an expression for the distance the block slides before stopping. Okay, well, here we're gonna, let's use Newton's second law here. So we're gonna have F, net force, equals ma. And then the only force here, once it gets to the bottom of the ramp and slides on here, on this horizontal surface, is just friction, the force of friction. So force of friction is going to be negative uk, and it's negative because it's opposing the motion. And n is going to equal mg because it's on a horizontal surface. So we're going to have negative mu k mg. So we're going to have ma equals negative mu kmg, so a equals negative mu kg. Okay, we have our acceleration now. Let's use our third kinematic equation, which is v final squared equals v initial squared plus 2a change in x. So what it stops, right? So we're going to have 0 at the end. We're going to have our initial velocity here squared. It's not negative anymore because it's off the ramp and it's going, it's continuing in the positive direction. And then minus 2 because it's negative times a, which is ukg. Let's change in x, and let's solve for our x here, which is going to give us v initial squared over 2 mu kg. There is our distance it travels before stopping on that horizontal surface. So for part E here, it says that the ramp now has friction. Same block is projected up with the same initial speed. It comes back down the ramp. So on the axis here, they want us to sketch a graph of the velocity while it goes up and back down the ramp, and it arrives at the bottom of the ramp at t final. And it wants us to label any intercepts, asymptotes, maxima, or minima with numerical values or algebraic expressions. Okay, so it's going to start at that v initial here. It's negative. And, well, like here, it's going to go up to 0. But since it has friction, it is not going to be 0 at Tf/2. Velocity is going to reach 0. The block is going to stop a little bit before that, actually. So let's draw a line up to before Tf/2, because the friction is working against the motion now. It's going up and gravity. And then now when it's going back down after velocity of 0, it's going to have a positive velocity. But the slope here of the positive section when it's going down the ramp has to have a smaller slope than the one when it has the negative velocity going up the ramp, because the areas have to be equal, because the area equals the displacement. So let's draw that with a smaller slope. So this area has to be equal to this area, because this is the distance it goes up the ramp, and this is the distance it goes down the ramp, which is equal. So these two areas have to be the same, therefore the slope here has to be smaller than the slope on this section here. So let me just write that here. So areas are equal. Alright, so there we go. That is the 2015 AP Physics C Mechanics FRQ number 1. Thank you for watching.